Hi, on this video I'm going to talk through questions 2 and 3 on your recent assessment. Question 2, it was supposed to be an easy question, but the situation was just a little bit confusing because you had these two masses that were connected and they were attached by this string. So initially they're at rest. A is projected with a particular velocity away from B. So really what we've got here, it's a mechanism for a momentum question. And this whole business about the string becoming taut, because it's light and it's inextensible, so you've got no kind of weird kind of forces there due to elasticity in the string. All that is meaning is that when the string becomes taut, both A and B are moving at the same speed. So before A is moving with a speed of 7.2, A is moving at 7.2, B is not moving. Afterwards, they both have the same velocity. So what you've got there, you've got a classic momentum situation. This was a conservation of momentum question, and it's talking about impulse there. Which should have been giving you a little bit of a clue. There are a couple of people who tried to do it using energy. Conservation of energy, okay, that's a given, but you were just focusing on kinetic energies. The kinetic energy isn't necessarily constant. There are other things happening. Okay, no friction, no elasticity, but you still kind of might have, sound. There might be all kind of things happening. And if you look down at part C, it says find the loss in kinetic energy. So you know from that there's going to be no conservation of kinetic energy, and it's just a dangerous assumption anyway. So it's momentum. Now, what I don't think I saw very much of at all was diagrams. Now, this was a simpler one. I mean, certainly when it comes to the last question, we had to use momentum as well. Diagrams. I show what's happening before, I show what's happening afterwards, and I'm really just using it. It's not particularly illustrative, it's just a way of organising the information, what's going on. I mean, there, I haven't drawn the string. I put them at the same distance there and there. I will put the directions on there though, but what I've got very clearly, I've got what A is going that way, velocity is 7.2, 3.6 kilograms, B 2.4 kilograms, it's not moving. And then I haven't drawn the string in, don't need to. I have interpreted that information and put a speed of V for both A and B afterwards. And then I just write down my momentum equations. Here, the momentum 7.2 times by 3.6, okay, plus 0. I know momentum before is equal to 3.6 V plus 2.4 V. I can see there I've just got one unknown. I'm just reaching for my calculator because I haven't written down what 7.2 times 3.6 is. 25.92. Adding those two, that gets me 6V. So now we do division. So V is 25.92 over 6, which is 4.32. Okay, so the second one, impulse. Impulse is change in momentum of A. So that means we need to look at what the momentum is after, well, it's not really a collision, is it? But the momentum after the string becomes taut minus the momentum before the string becomes taut. So mass before, velocity after, mass is the same. Mass times the velocity after minus mass times the velocity before. And note that the answer is negative. Now the mark scheme says something very specific about this. It says, well, it gives the answer as negative 10.4, but then it says it could be 10.4 Newton seconds towards B, or you could have 10.4 if that was the opposite sign to the initial velocity. Okay, so here in this calculation, that's negative, that's positive. So if you'd have had that, I'm just kind of pausing there. If in that calculation, but that gives me a negative. So must be opposite sign to the initial velocity. So I may have been a bit lenient on some people there. I think if you had the calculation the other way around, then that would have been positive. Then that would have worked, wouldn't it? Apologies. So if you'd have had the calculation 7.2 times by 3.6 minus that other one, maybe I shouldn't have given you that mark, because that would have got you positive 10.4, and that would have been the same sign as that. Okay, might have to take some marks off. The last part, I won't, of course. I just want to emphasise the fact that you just need to be careful of that sign. And the last part, find the loss in kinetic energy. So here, total kinetic energy before. So I've got half times the mass of A times by 7.2 squared, so half mv squared. Now, of course, after, there are two components to it. So we have got a half mv squared for A, but then we've also got a half m, so the mass of B is 2.4. That has the same velocity. You could, of course, combine that. You could just have it as an overall half times 6 times 4.32. But many of you missed out on a mark here because you just, I think, considered A. You just considered what A was contributing to the kinetic energy afterwards, and not the total. So it says, find the loss in kinetic energy. So it doesn't mean acting on A, it means as a result of the string becoming taut. So you want the whole lot, you want that whole action. So it's that first one minus that second one. So if you subtract these, you get an answer of 37.3, and of course it's energy. So we're looking at joules. Here they weren't as worried about direction, so they were quite happy for you to put negative 37.3, but that's the one where direction was important. Okay, right, number 3. Car mass power, we've got a little bit of resistance motion happening in there as well. Essentially, you were looking at two equations. Firstly, F equals ma, but remembering its resultant force in the direction of motion equals mass times acceleration. And then this other one here, sorry, I tend to think of it as a driving force, but tractive force is what's kind of in the book, and it's what lots of you wrote down, so I'll try and stick to that. Tractive force is equal to power over speed. That's obviously the most useful form for this question. Again, I've drawn a diagram. You know, lots of you don't like drawing diagrams. I mean, it's not a very detailed one, and certainly not a very successful one of the car, but I can there see what's going on. In particular, it's going to help me to think about what's happening when I've got the greatest possible steady speed. It's going to help me to think about the resultant force. Initially, I know that when the speed is 10, the acceleration is equal to 3.3. So I know, of course, what the power is, and I know what the speed is, so I can work out the tractive force. And I know it's travelling in that direction, so the tractive force minus the resistive force is equal to the mass of the car times by the acceleration. So tractive force, 60,000 over the speed, which is 10, minus the resistive force, don't know that. That's going to be equal to the mass of the car, 1,500 multiplied by the acceleration, which is 3.3. 6,000 minus the resistive force is equal to 4,000 and something, 4,950. So I can work out the resistive force. 6,000 minus 4,950. Now, based on this model, it is assuming a constant resistance of motion. So no matter how quickly we're going, this is fixed. So what we can do now is think about what the greatest possible steady speed is. Now, this is something you've done in normal maths as well, but you know that we have the maximum speed once it's finished accelerating. If it's accelerating, then there's always going to be a maximum speed just a little bit further along. So acceleration is 0. If the acceleration is 0, forces are balanced, so tractive force is equal to resistive force. The resistive force, 1050. Tractive force, of course, this is going to be for the maximum speed here. The maximum power, that is a constant. 60,000 divided by Vmax is equal to that 1050. So we just need to divide those. 60,000 divided by 1050. And we get that the greatest velocity is 57.1 meters per second. Okay, so that's based on a constant resistive force. In part B, it's a more refined model. The resistance to motion is proportional to the speed of the car. Now, I was a little bit surprised when I looked at the mark scheme. You know how proportionality works. That means we've got some constant times by the velocity, so that is the resistive force. You didn't get a mark for that. You got your first mark by putting it all into the kind of equation. So it's going to be a similar idea to this. We've got 60,000 over 10 minus the resistive force, which is that kV is equal to, and that there, I'll just write down as 4,950. Again, I could have just put in my 10 there, couldn't I? So I know that when the velocity is 10, we've got, I've put the 10 in there, I need to put it in there as well. So this time we are going to get, if I subtract those, we're going to get 1050 is equal to 10V, 10K. So K is equal to 105. So if we now again use this same statement here, I know that instead of that equation here, I'm going to get that the refined maximum velocity is equal to 105 times by the velocity. Should we just ditch the maxes? It's a bit silly, isn't it? So then V times by V, divide by that, I get that V squared is equal to 60,000 over 105. V squared is 571.4, so V is 23.9 meters per second. 5 marks there. You actually got, I think I've already said, you got 1 mark here, accuracy mark there, method mark, you got an accuracy mark for the 105, a method mark for putting it back in there, and then 2 accuracy marks, 1 for that stage and 1 for that stage, which just seemed a bit odd, because if you get that accuracy, you'd have to do something very wrong to get that one incorrect. Now, this here, I don't think anybody got 2 marks. I'm not even sure how many people got 1 mark, very few people. There are 2 marks. It's asking you about 2 specific models. It's asking you about A and B. So surely it makes sense to write down 2 separate comments, one about A and one about B. Now, it was very, very clear in the mark scheme, and sorry, I have got this, I might email it round again because I think this is really quite blurry. But it says, do not allow A and B are not very accurate. Neither model is accurate. You're not even allowed to say that model A is not very effective. what it's saying is a ideal answer is, and I'm just looking for, here it is. So this is from the examiner's report. What we are looking for is whether or not the model gives a good approximation or a good fit to friction in real life. Therefore, comments such as A or B is not accurate did not earn any marks, as they do not say anything meaningful. You wanted a meaningful and distinct comment. To gain marks, you needed to note that A is a very poor model for the friction, as the predicted speed was very inaccurate. So saying inaccurate wasn't good enough. You had to qualify it and say very inaccurate. And then you have to say B is a good model, as it is predicted, as the predicted speed is close to the actual figure. So one thing saying that A was really not very good at all, not very accurate, and then a separate comment saying that B was a much better model, and give a reason why. It's not very kind of tricky. It's a much better model because it gives an answer that's closer to the actual value, which is 21.6. So 2 marks. Even a 1 mark explain, I know it can take quite a lot of getting, but for that 2 marks, you just needed to write more. You needed to write more, and I know you were particularly under pressure for time for this exam. Okay, so I will post another video shortly on the